All right, hi, I'm Katya or Kitty, and this is our presentation on magnetic induction. And sorry for any background noise that may occur throughout the presentation. But anyway, I'm going to be starting with induced EMF and working through until an EMF in a moving conductor. And then on we'll cover the rest. Okay, so let's get started. All right, so let's start with induced EMF. So when a magnetic field creates a current, there has to be an induced EMF to be able to create that current. And so the magnetic flux needs to change for that to happen. And so there are three ways that the EMF can be induced in a loop. So there can be a change in the area, change in magnetic field, and change of the angle, which we will get into more in depth in the next slide. So, as you can see, as said before, a change in magnetic flux induces an electromagnetic force. I don't know why this is motive, opposing that change, which is a process known as induction. So, as said before, there can be a change. You can change the magnetic field within the coil. You can change the area of the coil, so you could move it in or out of the field, or you can stretch it. Or you can change the angle between the magnetic field and magnetic field direction, so wherever it's going, and the coil by rotating the coil. So this equation is known as Faraday's law, which we will get into in depth in the next slide, which basically shows how to calculate the EMF. So yeah, as we can see, Faraday's law of induction, this law predicts how a magnetic field will interact with the circuit to produce an EMF. So as we can see here, EMF equals negative N delta phi over delta T. So N would be the number of turns in that coil. Phi is also equal to BA, which is magnetic flux. And this is broken into B is the external magnetic field, and A would be the area of the coil. So this negative sign is related to Lenz's law, which we will get into in the next slide. So, yeah. But as you can see here, this is the coil of wire, and this is the induced current. So coil of area A with N turns, and this is the magnetic field, and it's going this direction. So a coil of wire moving into the magnetic field is an example of the EMF generated according to this law. So the current will create a magnetic field, which opposes the buildup of magnetic field in the coil, which, as we move on, Lenz's law, which states that the direction of the current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field. So, as you can see in this diagram, if you try to increase the flux, the induced field will oppose that increase. And in the other case, if you try to decrease the flux through the loop, the induced field will replace that decreased. So, as you can see here, the B field induced will replace this, and the B field induced here will oppose it by going this way. And this way it would be replacing the decrease, and this way it's imposing the increase. All right, EMF induced in a moving conductor. So when a conductor cuts through lines of magnetic flux, such as here in this conductor, the EMF is induced in that conductor. So as you can see here in this figure, this is cutting through the lines of the magnetic flux. So then an EMF would be induced right here based on the galvanometer. And this is an example of EMF induced in a certain moving conductor. So measurement of blood velocity from induced EMF. So if you're connecting all of this, you can see that this conductor will show the induced EMF. So, and the induced EMF does have a magnitude, so it will be able to measure the velocity, as this law, which dates back to Faraday's law, delta phi over delta t, which is broken into B, delta A, which is area, is magnetic field over delta T, and then this goes into BLV delta T over delta T, which equals to BLV. L is the length, V is the velocity, and then it shows how it works.